In computing, the modulo operation finds the remainder after division of one number by another. Given two positive numbers, or an n, a modulo n is the remainder of the Euclidean division of a by n. For instance, the expression 5 mod 2 would evaluate to 1 because 5 divided by 2 leaves a quotient of 2 and a remainder of 1, while 9 mod 3 would evaluate to 0 because the division of 9 by 3 has a quotient of 3 and leaves a remainder of 0. There is nothing to subtract from 9 after multiplying 3 times 3. Although typically performed with a and n both being integers, many computing systems allow other types of numeric operands. The range of numbers for an integer modulo of n is 0 to n-1. See modular arithmetic for an older and related convention applied in number theory. When either or n is negative, the naive definition breaks down and programming languages differ in how these values are defined. Remainder calculation for the modulo operation. In mathematics, the result of the modulo operation is the remainder of the Euclidean division. However, other conventions are possible. Computers and calculators have various ways of storing and representing numbers, thus their definition of the modulo operation depends on the programming language and/or the underlying hardware. In nearly all computing systems, the quotient q and the remainder r of a divided by n satisfy. However, this still leaves a sign ambiguity if the remainder is non-zero. There are two possible choices for the remainder, one negative and the other positive, and there are also two possible choices for the quotient. Usually, in number theory, the positive remainder is always chosen, but programming languages choose depending on the language and the signs of a and or n. Standard Pascal and Algol 68 give a positive remainder even for negative divisors, and some programming languages, such as C90, leave it up to the implementation when either of n or a is negative. See the table for details. A modulo 0 is undefined in the majority of systems, although some do define it to be a. Many implementations use truncated division, where the quotient is defined by truncation q equals trunc, and thus according to equation the remainder would have same sign as the dividend. The quotient is rounded towards 0, equal to the first integer in the direction of 0 from the exact rational quotient. Donald Knuth described floored division where the quotient is defined by the floor function q equals a n, and thus according to equation the remainder would have the same sign as the divisor. Due to the floor function, the quotient is always rounded downwards, even if it is already negative. Raymond T. Boot describes the Euclidean definition in which the remainder is always non-negative, 0r, and is therefore consistent with the Euclidean division algorithm. This convention is denoted always positive in the table. In this case, or equivalently where SGN is the sign function, and thus, Common Lisp also defines round division and ceiling division where the quotient is given by q equals round and q equals a n respectively. IEEE 754 defines a remainder function where the quotient is a n rounded according to the round to nearest convention. Therefore, the sign of the remainder is chosen so as to be closest to 0. As described by Li-Gen, Boot argues that Euclidean division is superior to the other ones in terms of regularity and useful mathematical properties. Although floored division, promoted by Knuth, is also a good definition, despite its widespread use, truncated division is shown to be inferior to the other definitions. Don Li-Gen, Division and Modulus for computer scientists. Common pitfalls. When the result of a modulo operation has the sign of the dividend, it can sometimes lead to surprising mistakes. For example, to test whether an integer is odd, one might be inclined to test whether the remainder by 2 is equal to 1. Bool is _odd, return n% 2 equals 1, but in a language where modulo has the sign of the dividend, that is incorrect. Because when n is negative and odd, n mod 2 returns -1, and the function returns false. One correct alternative is to test that it is not 0. bool is underscore odd, return n%2 equals 0, or, by understanding in the first place that for any odd number, the modulo remainder may be either 1 or -1. Bool is underscore odd, return n%2 equals 1, n%2 equals -1, modulo operation expression. Some calculators have a mod function or similar, expressed as mod, for example. Some also support expressions that use %mod or mod as a modulo or remainder operator, such as a %n or a mod n or equivalent. For environments lacking a modder performance issues, modulo operations might be implemented such that a division with a remainder is calculated each time. For special cases, there are faster alternatives on some hardware. For example, the modulo of powers of 2 can alternatively be expressed as a bitwise an operation. x%2n equals xn. Examples: x%2 equals x and 1, x%4 equals x and 3, x%8 equals x and 7. In devices and software that implement bitwise operations more efficiently than modulo, these alternative forms can result in faster calculations. Optimizing compilers may recognize expressions of the form expression %constant where constant is a power of 2 and automatically implement them as expression n. This can allow the programmer to write clearer code without compromising performance. Because if the dividend is negative, the modulo will be negative. However, expression n will always produce a positive result. So special treatment has to be made when the dividend can be negative. Equivalencies. Some modulo operations can be factored or expanded similar to other mathematical operations. This may be useful in cryptography proofs, such as the Diffie-Hellman key exchange. Identity. Mod n equals a mod n. Nx mod n equals 0 for all positive integer values of x. If p is a prime number which is not a divisor of b, then abp-1 mod p equals a mod p, due to Fermat's little theorem. Inverse. Plus mod n equals 0. b-1 mod n denotes the modular multiplicative inverse, which is defined if and only if b and n are relatively prime, which is the case when the left-hand side is defined. Mod n equals 1. Distributive. Mod n equals plus mod n. Ab mod n equals mod n. Division. A, b mod n equals mod n when the right-hand side is defined, not defined otherwise. Inverse multiplication. Mod n equals a mod n.